As we look further into the nuclear paradox as part of our Citizenship for Global Awareness series, we will use this video to set the stage for students to have an understanding of the difference between nuclear power for generating electricity and nuclear power as weapons. Let's start from the beginning. At one point in time, we've all learned what matter is. Everything is made up of matter, and matter is defined as anything that has mass and takes up space. We move to the idea of an atom, and an atom is the basic building block of matter. They contain protons with positive charges, neutrons with no charge, and electrons with a negative charge. The mass of the proton and the neutrons are very similar, with the mass of the electron being very small comparatively. The proton is what is used to organize the atom to the periodic table of elements. We continue with our review by identifying what are isotopes. Isotopes have the same amount of protons but different amounts of neutrons as seen here with carbon. If the number of protons is equivalent to the number of neutrons and electrons, then the atom is considered stable. But when there is more neutrons, then it becomes unstable. Radiation is a transfer of energy. It is important to understand this because the transfer of energy happens in multiple ways. One is the idea of conduction, where there is direct contact. You have convection, which is the mixture of fluids. You have the idea of advection, which is the mixing of fluid horizontally. And finally, the one that we are interested in the most for this topic, radiation. And that goes through a medium. And by medium, we mean water, air, or even a vacuum. Light, heat, sound, radio signals, X-rays are all considered radiation. As a further review, we look at the idea of ionization. If an electron that surrounds the nucleus is pushed out of its orbital, we call this ionization. This is seen here with two water molecules combining to form hydronium and hydroxide. So ionization is considered radiation because it is releasing energy. Radioactivity is a term used to describe the natural processes of atoms spontaneously disintegrating, emitting particles and energy as they transfer to different, more stable atoms. Alpha radiation is the least penetrating and is released by atoms such as radon. It can be stopped or absorbed by a sheet of paper. Beta radiation comes from the electrons that are not attached to an atom. It can penetrate air and paper. It can be stopped by a thin sheet of aluminum. Gamma radiation is the most penetrating because it has the shortest wavelength. Even small levels can penetrate air, paper, or thin metal. Higher levels can only be stopped by many centimeters of lead or many meters of concrete. As you can see from this diagram, radiation occurs to us in all aspects of our life. Only very small parts are actually artificial sources. So if we're talking about nuclear energy, we need to end up identifying what is uranium. Uranium is a very heavy metal which has been used as an abundant source of concentrated energy for 60 years. Uranium occurs in most rocks in concentrations of 2 to 4 parts per million and is common in the Earth's crust. Like other elements, uranium occurs in several slightly different forms known as isotopes. These isotopes differ from each other in the number of uncharged particles, neutrons, in the nucleus. Natural uranium, as found in the Earth's crust, is a mixture largely of two isotopes, uranium-238, accounting for 99.3% of uranium, and uranium-235. Uranium ore can be mined by underground or open cut methods depending on its depth. After mining, the ore is crushed and ground up. Then it is treated with acid to dissolve the uranium, which is recovered from solution. The economic viability of uranium mining is often largely dependent on the method of recovery. Conventional methods involve excavating, processing, and extracting uranium into a fluid from which yellowcake can be concentrated. In situ recovery methods are relatively inexpensive compared to conventional methods because in situ recovery avoids costly excavation as well as milling, heap leaching, and expensive reclamation. This map indicates the places where uranium is present in the continental crust. The green is actually the largest concentrations, followed by yellow, then red. From the table you can see that there are many countries that have enrichment capacity. The US has multiple facilities, but the Russians are still the ones who are actually producing the most amount of enrichment. Here are nuclear fuel cycle facilities in the US. Piketon is a gas centrifuge which actually produces enriched uranium. This facility is not operational at the current moment. We here will look more at fission, which is the idea of breaking apart. Nuclear fusion is actually where you're trying to bind it together. Both of them produce energy. Reactors start with uranium-235, which is extremely rare. Only about 0.7% occur in nature. In a fission reactor, a neutron is slammed into an atom of uranium-235, resulting in the unstable uranium-236, which then breaks down in other fission products and neutrons. The result is continued bombardment of neutrons into an atom that are left over, releasing energy every step of the way. Uranium is significant because it is one of the radioactive materials, as indicated by this periodic table of elements. All the elements in yellow are considered radioactive. Here you can see that the three-phase thorium reactor, which takes uranium-235, it is bombarded with neutrons, it moves to uranium-238, then decay allows it to become plutonium-239. 239 goes to thorium-232. Thorium-232 moves to uranium-233. Uranium-233 back to thorium-232, and then back to uranium-233. So after all of this background information, we want to talk about how the energy goes into a power plant. Many people look at this site and they think that this is a very large nuclear power plant, but in reality, these are cooling towers that are used at many of the major facilities that produce electricity. In Ohio, nuclear power plants contribute $521 million to the state GDP and account for nearly 3,600 direct and secondary jobs. If we look closely at Ohio, we have actually 3 nuclear power facilities most people are unaware of. This is the Davis-Besse plant, which is a pressure water facility. This is the Perry nuclear facility, which is a boiling water reactor. And this is the Beaver Valley pressure water reactor. It actually has 2 reactors on the sites. As of April 2017, the United States had 100 commercial reactors in operation, 34 boiling reactors, and 66 pressure reactors. The operating principles are similar in that water is heated to turn a turbine that generates electricity. This diagram indicates the commercial nuclear power reactors that exist. There are other reactors that exist in the U.S., and these are test and research reactors as indicated here. There are 31 of them that are operational currently. These reactors use fuel rods. Fuel rods are used to efficiently manage radioactive material that are used in the reactor. Fuel rods start as a pencil eraser sized pellet. They are stacked into a tube that is referred to as the cladding. The cladding is sealed and now referred to as a fuel rod. Between 100 and 300 fuel rods are assembled into a square and are considered to be the fuel assembly. Between 150 and 250 fuel assemblies are placed in the reactor pool. The fuel assemblies then heat the water to create electricity. Fuel assemblies are replaced every 18 to 24 months. Spent nuclear fuel is removed from the reactor and placed in a storage tank that is full of water. The vessels are placed in a box that is made from neutron-absorbing boron. This allows the rods to cool down before placed into a dry cast on the site. Dry casts are located on site until permanent storage can be identified. This is considered safer than leaving a high concentration of fuel rods in the same location. Dry casts use the natural convection cycles to cool the rods further. The number of dry casts are regulated by the federal government. Most states do have license to store spent nuclear fuel, but a solution for long-term storage has not been agreed upon. It is very rare to see a new licensed nuclear reactor to come online. Just for licensing approval, a company would be looking at $75 million before construction can commence. So here is the nuclear paradox. The weapons grade versus power grade. We just talked about the idea of how nuclear energy can be used to produce electricity. But the uranium-235 is only in 3 to 5%. To make it weapons grade, you have to have 90% uranium-235 to go through the reaction. In order to do this, you have to use a centrifuge process. There's very little difference between uranium-235 and 238, but the small amount of mass change is able to be separated out when you use a centrifuge. But you have to use many centrifuges because the number is so small and the elements are so light. These centrifuges over time allow the U-238 to be isolated from the U-235, and that is what makes weapons grade uranium.